Alright friends, today I'm going to be taking you on Hardy-Cross method of a moment distribution. Before we continue, you have to arm yourself with these formulas and special cases involved in Hardy-Cross method of a moment distribution. In fact, general method of moment distribution, including Hardy-Cross, Clapeyron's theorem of three moments, and the slope and deflection method of a moment distribution. First, you have the number 1 here, that the fixed end moment of any beam or any structure you're taking into consideration is WL squared over 12 for a UDL, uniformly distributed load, and WAB squared all over L squared for point load when the side-by-side distance of the point load from the joints are not equal, and WL over 8 for a point load when the point load is equidistant from the opposite joints holding the span in place. And the second special case is that the clockwise moment is positive while anti-clockwise moment is negative. Then the third is ultimate span moment or maximum span moment is equal to WL squared over 8 for UDL, WAB over L for PL when the side-by-side distance of the point load from joints are not equal, and WA squared over L or WB squared over L for a point load when the point load is equidistant from the opposite joints holding the span in place. Then the fourth is effective span moment. This is done using superposition principle by subtracting half of the support moment holding the span in place from the ultimate span moment. This I will demonstrate and you will understand what I'm talking about here. The fifth is the area and centroidal distance. This is about the area or the area of the hemispheric and triangular shape caused by UDL and point load respectively, and the centroidal distance of these shapes. As you can see, uniformly distributed loads usually generates this form of shape, is hemispheric here, whereby this kilonewton per meter is the load employed on this span, which generates this effective span moment here, which is a maximum span moment, which is H. It can be taken as the height while you are calculating the area of this shape. So the centroidal distance is given as L over 2, while the area of that hemispheric shape down there is given as 2 over 3. Or you can say 2 per 3 times base times height. Then for the point load, usually gives a triangular shape. This particular point load here, P in kilonewton, at the distance of A and B. You can see the distance is not equal when I talk about not equidistance or equidistant. You can see from here and here that the length of here to here is actually bigger than here to here. So the point load is not equidistant from the support holding it in place. Then the H, that's the maximum span moment that this point load generates on this beam, is at this point as it aligned to this place, and you have H is equal to H mass. Then the area of the triangle there is half base times height, while the centroidal distance is equal to L plus A over 3 or L plus B over 3. I think you have to arm yourself well with these formulas so that while we are doing the main job and the main work, you will not get missed out of the whole teaching. So depending on the span consideration, there are other shapes, but this is the most commonly encountered during the solution of moment distribution. I'm talking about the hemispheric and the triangular shape we have just seen. Then the sixth one is solve for shears. This can be achieved by taking moments about points and doing the arithmetics involved. This will end up yielding a general formula as we will discuss below. Then this is it here. This is how to calculate for shears. You bring out the beam in place, put the moment that is occurring at the end of the beam, bring the indicate where the load is occurring and indicate the distance at which it's away from the supports at distance A and B. Then the reaction that was taking place at one of the joints and the reaction that is taking place at the other. Now you can take moment about one of the joints, of which if I'm taking about A now, you have that P times A, this is the point load times A towards this A, plus you can see what I assigned here, that the clockwise moment is positive. So it means as P will take clockwise moment towards this point, it's giving me a positive. That's why I have P times A plus MB, you can see the direction of it, minus MA minus RB, that's the reaction here, times L. You can see the reaction here is going anti-clockwise, is equal to 0. So when you do the arithmetic involved, you end up getting this formula. And this formula is of my interest to tell you that it's a general formula for point load, for the shears of a point load occurring on a beam. Then for a UDL load, you would use the same method, and with what I wrote from these places, I think it's easy to understand. You end up generating this formula here on a red, and this general formula, without having to draw all these things, once you bring out your beam and insert into this formula your details you already have, I think will be giving you a reaction at a particular point of which you're looking for it at. So having done all those ones, I think we have to get into Hardy-Cross method of a moment distribution. Here on this video, I think I will explain the Hardy-Cross method of moment distribution, and on the next video coming up, I will solve an example with it, and you get to understand it more with what we are saying here. So the procedure for Hardy-Cross method of moment distribution includes: 1, you have to obtain your stiffness factor. We indicate it as K, and distribution factor, we indicate it as T dot F, where distribution factor is equal to K initial all over summation of K initial. So here you sum all the, don't worry, when I get to the example you get to understand this, but you have to have this formula offhand. Then calculate your fixed end moment, calculate your out of balance moment, which is summation of the moment at a joint. Obtain your balancing moment. This is done by taking negative of your OBM, which is out of balance moment, as balancing moment is equal to negative of out of balance moment. Then calculate your distributed moment. Here I wrote mathematically is dm is equal to bm times df, where dm is the distributed moment, bm is balancing moment, while df is the distribution factor. Then calculate your transferred moment tm. That tm is half of the distributed moment. Then repeat from step 3 to 6 until the distributed moment is significantly small. Then the 8th procedure is calculate the final moment at each joint using this formula here, where you have that the final moment is the fixed end moment plus transferred moment plus distributed moment. Remember, one thing here is that the out of balance moment is missed and the balancing moment is as well missed. Just sum these three: fixed end moment plus transferred moment plus distributed moment. You are able to get the moment distributed at that joint. When you use any other method, it will as well give you that moment. Or we will do it here. We'll solve one example with this method, and other methods I will as well solve the same example there, so that you get your answers confirmed and have confidence that the procedure is well taught. Then obtain your ultimate span moment and shear force. Then calculate your effective span moment. With these ones, I think when you get to this point, the question that you might have been asked must have been done. But if you want to go extra level, you can as well do all these ones. It's easy to do. And here we go. The example.